Okay, let's get started, everyone. So, any question from this time? Today we are going to talk about the application of quantum Fourier transform. So this time we said the quantum Fourier transform cannot do classical Fourier transform quite yet, but we can use it to do factoring. And here we are going to talk about the core part of doing factoring, which is another number theoretical problem. Okay, so we are going to use quantum Fourier transform to do this order finding really quickly. And after we show that you can do order finding, then it's just some number theory to show that you can use the order finding algorithm to do factoring. Okay, and so what's this order finding problem? It's this. Okay, so this is a totally mathematical problem. So you are given two integers, x and n, and n is bigger than x, and n is co-prime to x. Okay, so there is no common factor between x and n. And then you can show that there exists some r such that x to the r's power equal to 1 mod n. Okay, so this is just number theory. You can show that if x and n has no common factor, then there exists some r such that x to the r equal to 1 mod n, where r is a positive integer. Okay, and obviously if x to the r equal to 1 mod n, then x to the 2r, 3r, 4r, they are all equal to 1 mod n. Okay, and so we want to find the smallest one. Okay, so that's kind of the period of x when it's modding n. Okay, and so I guess let's go to example first. So what do we mean by the brute force order finding algorithm is just you keep multiplying x with itself. Say you have x equal to 3, n equal to 7, then you just keep finding higher powers of x. So x squared will equal to 3 times 3, and it's 2 mod 7. Then you have x cubed, so you multiply another 3, and it's 6 mod 7. And the x to the 4th is 4 mod 7, and the x to the 5 will be 5 mod 7. And finally, you see that when is r equal to 6, so x to the 6 will be 1 mod 7. Okay, so you know r is 6 here. Okay, so yeah, so this is some small example of order finding with yeah, x equals 3, 7, n equal to 7. So you see you keep multiplying x by itself, and at some point you will see x to some power equal to 1 mod n. Okay, and that power, so this 6 here is the r, is the order we want to find. Okay, so we want to do order finding for any pair of x and n such that x and n co-prime to each other. And so then we define a bit of notation here. Okay, so we will want this L here. That's the number of bits to write down n, and that's basically log n take a setting. Okay, so this L we think is a problem size because x is smaller than n, and yeah, so and this thing should be really scaling with how big n is. And yeah, and this number of bits of n is how many bits you need to basically write down this problem. So this is a problem size. And now with respect to problem size, we think about classical algorithm and quantum algorithm. And so there is no known classical algorithm to solve this in poly L. Okay, and yeah, we just don't know how to solve this efficiently classically. And we are going to show that there is a quantum algorithm that solves this problem in order L cube number of operations. Okay, and so you see this is much faster. And so classically, this is about 2 to the L, because classically, basically, you need to keep doing, basically the best known algorithm is this brute force algorithm, and this requires the basic order n time, which is order 2 to L. Okay, so classical base known is 2 to L. Let me try to write it with my mouse, 2 to L. Okay. And then quantum we have L cube, so you see this is exponential speed up. And as we said, if we can do order finding, then it's just some number theoretical reduction to show that you can do factoring by doing order finding. Okay, And but let's now get back to this part. Okay, so we are going to spend the whole class showing you how can you have a quantum algorithm solving order finding in very fast in poly-L. Okay, so that's order finding. And yeah, then we have a quantum algorithm of order finding, and it's really just one line, so it's really short. The important part is you apply phase estimation on this unitary, that's multiplication by x. Okay, multiplication by x method. Okay, so really this is the order finding algorithm. You do phase estimation on this unitary ux, and ux is defined by you see it's just multiplication, so ux x on some y, then it becomes some so we define ux on every computational basis y, so ux on y become xy mother. Okay, so ux is really an n by n matrix. I should say yeah, ux is really an n by n matrix such that okay, because the computational basis is y here, y is mother, and yeah, y is mother, so y is between 0 and -1, so this is an n by n matrix, and also we want the x to also between 0 and -1, because we say GCD xn equal to 1. So I guess, but it's really weird to multiply by 0. So I guess x should actually become 1 to 1 to n minus 1. Okay, so maybe that's so x really from 1 to n minus 1. Okay, and yeah, so that's a very classical unitary. That's just doing multiplication. So you multiply everything in the input to multiply by x. Okay. And then we need something extra, so we want this thing to be unitary. Then, then basically you need to be reversible, and that's where this GCDxn equal to 1 come in. If GCDxn equal to 1, then you can show that this is reversible, and actually it's unitary. Okay, and yeah, so this will tell basically doing this will find the order, and but that sounds very weird. Probably feels weird. And let's see, get some intuition of why does this thing find the order of yeah, why does doing phase estimation on this ux find the order of x. Okay, so ux definitely depend on x, but why does you tell you this r, which is x to r equal to 1 mother. Okay, and then we remember that for the phase estimation, yeah. So yeah, there are a lot of questions, but let's look. Let's take a bit of a review of phase estimation. So we remember phase estimation says that you have some unitary u, which will be this ux, and you have some eigenvector small u, and the phase estimation will find the phase e to the 2 pi I phi. Okay, this eigenvalue to this eigenvector, and then basically we'll find this phi. And yeah, so you see that we have phase estimation is an eigenvector, and then maybe the first thing we need to think about is what's the eigenvector to this ux, and well, let's give you an eigenvector of ux. So eigenvector is something ux acting on the eigenvector doesn't change except getting a phase. And so one way to get the eigenvector, which is not normalized for the simple notation, is this thing. So you think about because you think ux is going to multiply the y direction by number x. Okay, so if you just start with x and you acting and ux, you will get x squared, and you just summing all of those things together. So you just have an equal superposition of x squared, x cubed, all the way to x to r, which we know equal to 1. Okay, yeah, so by definition, x to the r equal to 1. Then we think about what happened if you have an equal superposition of all the possible powers of x. Then you see that you add ux on this thing, then this x become x squared become x cubed, xr minus 1 become xr, and this xr x by another u become xr plus 1, which is just equal to x, because x to the r is already 1, and then 1 multiplied by x become x. Okay, and but you see this state is just a cyclic permutation of this state, right? You just you just have a different order of summing the whole thing. You are still summing over from x to the 1 to x to the r. So this is x1 to summation of x1 to the xr, and this is summation of x1 to x3 all the way to xr. And summation doesn't take care about the ordering, and so really this state is same as this state, because this applying ux just do a cyclic permutation. So you see this state, we call it u0 is the eigenvector of ux. Okay, and then we see that, okay, so this cyclic permutation idea is nice to control eigenvector of ux, and actually we can control more of those by multiplying some phase on those x to the some power. Okay, and excuse me, and yeah, so we also want x to the some power, and so how about we put some phases between those x to the some power, and in particular have the phase being, excuse me, omega equal to rth root of 1. Okay, so omega equal to e to the 2 pi over r. Take a minus sign so it's easier. Okay, and so we define this u1, which is omega to the x plus omega squared to the x squared plus all the way to omega to the rxr. And then we think about what happened to u1 if you apply ux on it, and then you see that x become x squared, x squared become x cubed, and xr minus 1 become xr, and xr become x, just because you multiply all those by 1x, and then you try to make things together, then you see that, yeah, and then you see you try to match up those terms. So you see omega's so this omega squared x squared become omega x squared, and this omega squared omega cube x cube will match up with omega squared x cube, and all the way to and this omega to the r x to the r become omega r minus 1 x to the r, and omega x become omega to the rx, which is equal to just x, because omega to the r equal to 1. This is just x. And so what we see is that, so for every basis, so for every x to the k, the number of omega get you get 1 less omega. So this omega squared becomes just omega 1, and the omega cube will just become omega squared. Omega r minus 1 become omega r become omega r minus 1, etc. And omega r become just 1. So every term get multiplied by omega minus 1. Okay. And yeah. And so you see that u1 actually has eigenvalue omega to the minus 1, which is equal to this. So this is why we have minus sign here. So it has an eigenvalue e to the 2 pi I over r. Okay, so I'm drawing right now. Okay, and next, then you have some things that's different number mod n. Okay, so you just have equal solution of the orbit of x or powers of x, and then you can multiply it with some power, and when you apply ux on it, you will permute those secret permute those power of x, and in the end you will get some factor that's omega to the some power. Okay, so here we have u1, and then you can think about you have u2. Then if you have u2, then it will be like you have omega squared. If you have u2 and so it's hard. So you have omega squared x plus omega fourth x squared plus, so each time you get extra omega squared, and then you will see that you apply ux on u2, you will get omega minus 2 on u2, and so that gives you e to the minus e to the plus 2 pi 2I over r, okay, etc. Okay, so you see that you can find a lot of eigenstate for u, and in particular, so we will find r different eigenstate for u in this way. So you can have different phase from omega to the 0, omega to the 1, omega to the 2, all the way to omega to the r minus 1. Those will be different u, and if you write down everything properly in a complex notation, it will be this way. Okay? So we want to actually write the normalized eigenstate. Then we have I guess I should be a little careful because we didn't normalize here. So this is I guess let's do a tilde on everything. Okay, because we didn't normalize here. Tilde. Okay, so if we normalize and everything, then we can write r different state, and they are indexed by those s, and as we say, s from 0 to r minus 1. And this s is the number of omega you multiply by x. Okay, so s equals 0, you don't multiply any omega, and s equals 1, you multiply 1 omega on x and omega squared on x squared. And s equal to 2, you will multiply omega squared on x and omega force on x squared, etc. Okay, so those r different eigenstate are indexed by this s, and the total state is 1 over square root r. This is for normalization, and summation k from 0 to r minus 1, so all the possible power of x to the k until you go back to 1. Okay. So k equals 0 is just 1, and k to r minus 1 is the biggest possible power. And then you have phase here. This is exponential minus 2 pi over r s times k. And so this is basically omega to the, in terms of omega, this is omega to the s times k. Okay, so just what do we do here? What we done before. So yeah, this is the state. The eigenstate we found, okay, and ux have more eigenstate, but those are all we need. Okay, so we found that r different eigenstate over ux. Okay, and any questions so far? Yeah, and so we do our check again. You apply ux on this us for some s, then you see that you apply ux. Then you get HR x on the computational basis here. So x to the k becomes x to the k plus 1, and because everything is cyclic, so you can change the if you do change a variable on your summation, so you change k to k minus 1, then you see that you get the HR factor of this omega to the minus s. So this yeah, you change this k to k minus 1, then you will get the HR factor of exp 2 pi over r times s. Okay. Yeah, and so that's our intuition written in more formula here. Okay. And so finally, so we have done that downward analysis of some eigenvector of ux, and let's assume that we have some us, and we see that if we apply phase estimation of ux with this us, then we will get s over r, because that's just phase estimation too. The phase is exponential 2 pi s over r, so you do phase estimation, we will learn s over r. Okay, so then that's very nice. So this thing is almost r. You also know s, then you can know r, right? Okay, so this thing has information about r. But then we run into trouble because yeah, so if you want to do this, then you need to control us. But if you want to control us, that's pretty hard, because say us is basically equal to coefficient of all the powers of x, and yeah, and if you want to control this thing brute forcefully, then basically you need to know r, because you do want to control x x squared all the way to x to the r, and create equal superposition between them. Okay, and that's very hard because you don't know r. Okay, so how do we not only not how do we do this phase estimation without knowing r? That's a problem we need to solve. Okay, and but so now here comes the very interesting idea is well, you don't need to know r. If you don't know r, then you cannot get individual US. But you can actually get a superposition of a lot of US. Actually, you can get an equal superposition. Excuse me. You can actually get an equal superposition of all possible US by just writing down the state 1. Okay? So this is just a computational basis state 1. Remember, S is some superposition of a computational basis state with some phase. And you find out that if you have equal superposition over all the r different S, then that equal to 1. And I guess that's that's related to the Fourier transform we talked about, because you see that when you sum over different S, so if you sum this thing over different S, then you see that for the k that's for k equal to 0, I guess let's go back to here. So for k equal to 0, this is x to the r. You see that x to the r always has no factor between them. So it's always omega to the r to the summation. The thing we talked about before in the Fourier transform, that's this summation s, and omega to the s equal to 0. Yeah, s times to the times some k equal to 0 for k not equal to 0. Yeah, excuse me, I have a bad drawing. Okay, omega to the s times some k equal to 0 for k not equal to 0. Because remember in Fourier transform, we talk about, okay, so maybe let me try to, okay, the online people are not going to see this, but let me try to flash the previous PowerPoint really quickly. Let's see if I can do this. When we talk about actually discrete and Fourier transform, do this. No, I guess I need to stop this one. Keep and do this one. Okay. Yeah. Okay. And so let's do this very quickly. So remember we have this thing. We say that we sum over different power of e to the 2 pi jk over n, and when k not equals 0, and you sum over j, this is always going to be 0 because you are summing over this equal partition point over this unit circle on complex plane. So we have example n equal to 5 here. So when k equal to 1, then you are just summing over j is just 1, 2, 3, 4, 5. And when k equal to 2, you are summing over 1, 2, 3, 4, 5, etc. Okay? And yeah, so when k not equals 0, you are always going to sum over those endpoints and let sum equal 0. And the k equals 0, you are going to keep summing 1, 1, 1, 1, 1, and you are going to get square root n. Okay? And so that was what happening back here. Okay? So that was what happened here. So with that thing, you see that when you sum over different US, then all the k not equal to 0 component sum equal to 0, just because the Fourier transform summation coefficient summation to 0. Okay, and anyway, this is something you can check yourself. And if you see this is true, then even though we cannot control individual US, we see that we can control equal superposition of different US by just writing down this one state here. Okay. Yeah, so we can just have 1 here, and then now we see if we do so I guess we do phase estimation. First register 0, so this is the answer register, and the second register, this is the register where you put eigenvalue. So instead of putting some specific eigenvalue, you just put 1 on the second register. Okay, if you just put 1 on second register, then we know the 1 is the equal superposition of those are different eigenvalues. Sorry, these are different eigenvectors, and then then we know before that because phase estimation is a linear operation, then you are just going to get the equal superposition of different eigenvalues. Okay, and each one of them has eigenvalue S over R. Okay, so you are going to get equal superposition between different different eigenvalue tensor is eigenvector. So different eigenvector US and the eigenvalue S over R. Okay, and then now if S over R is not, so remember when we say phase estimation there was some precision issue. So if S over R is not a fraction of 2, then you can just take the precision you want. So if you take t equal to this 2L plus 1 plus log log 2 plus 1 over 2 epsilon, and so basically 2L plus 1 plus order log 1 epsilon number of bits on the first register, then you can get 2L plus 1 bits of precision with success probability 1 minus epsilon. And we are going to see that this 2L plus 1 bits of precision is enough to do the order finding. Okay, and yeah, but also another issue we'll get here is I guess not quite issue yet, and but here so you see that this US is equal to this 1 is equal superposition of different US with uniformly US, and so this resulting S over R you are also going to get a uniform S. So you are going to get S over R with a uniformly random S. And once again, S is from 0, 1 to R minus 1. And so yeah, so we are going to draw a uniform S over R, and then later we'll see how you're actually going to iterate R from there, from here. Okay, and question so far? And I guess let's do a bit more formal summary. Okay, so this is what we've done so far is this quantum order finding algorithm, and we have a sketch here because there are more detail we need to wrinkle out. And so with our input to our algorithm is so first is this black box U sub xn. So this U sub xn do this and we also just shorthand it as U sub x. I guess I should write U sub xn, sorry. Okay, so this U sub xn, yeah, this U sub xn acting on y, basically do multiplication, making on y become xy model. Okay, and we define L equal to log n, and then we also need to input integer x and t, where t is the number of bits we need to do on the first qubit. So t will be 2L plus 1 plus order log 1 over epsilon. Okay. And so this algorithm should output this order R of x, which is smallest integer R such that x to the R equal to 1 model. Okay. And the procedure start with this. Okay, so we basically do phase estimation, and there are 2 registers. And first register is where you write down the answer, it has t qubits. And the second register is where you do the multiplication, so this is where you act the UX on. So you need dimension big N, and we say that we need L qubit to write down this dimension big N. We need L qubit to write down N, and so there are L qubit on the second register. Okay, so this is computational base is 0, computational base is 1, but this is t qubit and this is L qubit. And then on the second step, we create the equal superposition on the, okay, so about the and the next 3 steps, this is where we do phase estimation basically, and we write down the detailed step of phase estimation to just kind of remind you once again what's happening. Okay, and it's over a detailed view of what's going on. Okay. And so second step, first we create the equal superposition on the first register, and basically you do headmap to the T on first qubit. I should say not say first qubit, I should say first register, sorry. Okay, so headmap to the T on first register, and this will create an equal superposition on the first register. So it become, well, there are 2 to the T different number here, so it's 1 over square root 2 to the T for normalization, and the summation J from 0 to 2 to the T minus 1, okay, or J. And then for the ease of notation, so for better representation, we also want to write this 1 in the as a superposition of different eigenstate of UX. Okay, and we know 1 is this equal superposition of all the s, and with normalization 1 by square root r. Okay, so this is a thing we stated before. This thing, so I guess this should be bigger because it's really important. Okay, 1 equal to this 1 by square root r summation over s us. Okay, so this is just equal because I just expressing 1 to different thing. Okay, and then we apply this uxn and controlled by first register. So we apply uxn to a j. So if first register is j, we apply uxn j times on the second register. Okay, and so in terms of computational basis, it will become this thing. Okay, so you apply uxn on 1, then uxn on 1, you just have x, and they apply j times, then it's x to the j, because, well, uxn is multiplying by x. Okay, but if you review this in the eigenbasis of uxn, so you write 1 as this us, then you see that uxn on us become e to the 2 pi I s over r. Right? This was this thing here. Okay, us is exponential 2 pi over r s times us. Okay, so each time you apply ux on this us, you get e to the 2 pi s over r, and then you apply j times, then you get extra j here. So then you see that in this eigenbasis, you get this extra phase e to the 2 pi s j over r. Okay, and yeah, and then we group the summation together. So we put this j inside and group the summation together. So we have a summation j, summation s, and all the normalization together, 1 over square root r and square root 2 to the t. Okay, so this is just apply ux on this part. Okay, and then we apply inverse Fourier transform on the first register. Okay, so what's on the first register is, okay, and yeah, so we kind of change the order of summation. So you keep the summation s outside, and you think about what's left for first register is those 3 terms that with color. So you have summation j from 0 to 2 to the t, and this factor e to the 2 pi I sj over r, and computational basis is j. Okay, and you apply Fourier transform, inverse Fourier transform, but you see that then there is some trouble. This is where the precision of inverse Fourier transform come in, because Fourier transform, you see, because now you see that the number state here is 2 to the t, because j is from 0 to 2 to the t. So here we have a bit of mismatch, because we have over r here. We have over r here because we were summing over s, and there are different s. But j, there are 2 to the t different j. And if you want to match this to the Fourier transform notation, you want e to the ijk over big N, right? Big N should be the number of j here, and big N should be 2 to the t. So big N is not r, but then you can do some elementary math here. So this sj over r is j times 2 to the t s over r divided by 2 to the t. So in this form, it will be the Fourier transform form. Okay, so I guess I should this is really hard. Let me try to pull up the previous slides again. So Fourier transform. Sorry. Oh, okay. It's fake. Not dead. Yeah. So Fourier transform here. You see that the Fourier transform we have e to the ijk over n k. Okay. And once again, this n is k from 0 to bigger minus 1. Okay. And so this is what we want. And let's go back to the previous slide. Okay, so we want to write this in the form of e to the ijk, e to the 2 pi ijk over n. Okay, and so we have e to the 2 pi here, and jk over n. Bigger n is 2 to the t, and there are two different big n, and that's a bit confusing. But this big n is different from the big n for Fourier transform. Okay, and but anyway, so we see that k is 2 to the ts over r. But for this to be exactly Fourier transform, we need 2 to the ts over r need to be an integer, right? Because we write Fourier transform, this k was an integer. Okay. But so this is where precision comes in. We say that if this thing is not an integer, and then we have a very high probability to find some integer that look like this. Okay, and so I guess I should put a setting here. Okay, and so this is an approximation here. So so you apply quantum Fourier transform, and you will get something that look like this. Okay. And you get then you measure the first qubit, you will get something about 2 to the t times s over r, and maybe with some rounding. Okay, and with the number of bits precision that you want. Okay, and so the precision issue we'll deal with later, but for now we see that we get 2 to the t times s over r. And we know what's t, so we'll get s over r, and then we'll get uniformly random s from 0 to r minus 1. Okay, and then we see that okay, and so we'll get a whole bunch of different s over r, and how we get r from them is that we are going to get different S0 over R0, S1 over R1, S2 over R2, etc. And then then you can get R by doing this multiple times and calculate the least common multiplier of those R0, R1, R2, the different R you get. And we're going to show that with a high probability you will get R from those things. Okay, any questions so far? This is a sketch of the quantum order finding algorithm. If you are okay with this, then let's go to the details. Okay, so there are 3 tricky points that we need to deal with for this order finding algorithm. Okay, and the first one is we need to do this U sub x to the j very efficiently, because we need to do a total multiplication of j here. And so if we just do those ux one by one slowly, then basically it's saying us doing classic algorithm, you need to multiply x j times, then that's just, you need to multiply x r times, then that's just too much. We don't want to multiply x possibly order n times, that's too much. And the way to do that is we want to implement u sub x to do a j very efficiently. I guess big example. Okay, and to do this, we do repeated squaring. So if we can do this efficiently, then we see that this apply control x part then can be done very efficiently. Okay, and that's the first one. And the second one is the precision issue we just talked about. Okay, so if if the 2 to the t s over r is not an integer, then so basically 2 to the t s over r not an integer, then our then our phase estimation algorithm don't give you the exact s over r. Okay, so for example, if your r is 500 and n is 1024, then you see that n s over r has a probability that has a high probability that it's not an integer. Okay, and yeah, so I should say maybe s equal to 1. Okay, so maybe s equal to 1. Yeah. Never mind. Yeah, so you have say this n is not divided by r. Then for a lot of s, this is not an integer, and then you have some precision issue. And how do you still find s over r? And this is where we use continuous fraction algorithm. And finally, this is something we kind of gloss over. We say we will find s over r, but what we are going to find s over r is kind of like a real number. We are just going to find s over r. We are not going to find a number s and a number r. And so this can have trouble if x and r has some factor together, so they are not comparable to each other. Okay. So for example, if you have r equal to 6, x over x equal to 2, and you find s over r is 2 over 6, but the algorithm is just going to tell you that 2 over 6 equal to 1 over 3, then you think r might equal to 3, right? So when you see you get s over r equal to 1 over 3, you are not sure whether it's s equal to 2, r equal to 6, or even like s equal to 3, r equal to 9, etc. Okay? And that can be troublesome, and that's why we need to run the quantum parallel algorithm multiple times. So you are going to find multiple here is another typo. You are going to find multiple si over I, and then and those ri can be different, okay? Because each I can have can come from r with different s and different s with different coefficient with r. Okay, so we're going to find a whole bunch of si over ri, and then just calculate the least common multiplier of ri, because all the ri should be some factor of the actual r. And so you find just enough ri and calculate the LCM between them, and you will have high probability of finding r. Okay, and yeah, so this is what we do. Repeat squaring. Okay. Yeah, and so I guess we have 5 minutes. So let's do the first part. So this is the easiest. Although I have a little bit of typo here. Okay, it's a repeat squaring. We want to find x to the r. Yeah, so we basically want to find x to the 2 to the j very efficiently, and we can do this by repeated squaring. That's sorry, I have a k. Should have k here. So many typo. X to the k. Okay, so basically, okay, so we do repeated squaring, and so basically, if you want to find x to the some power of 2, you just keep squaring two things together. So x squared equal to x times x, and x first you can just have x squared times x squared, and all the way to some x to the 2k equal to xk times xk, etc. And so for example, if you want to calculate x to the 16, then x to the 16, then that's equal to x to the 2 to the 4. And by this repeated squaring, you only need to do this 4 times, okay? So x to the 16, you can just do x squared equal to x times x, and x4 equal to x2 times x2. Oh, actually, so this is not 4 times. And 4 times, sorry. I'm confusing myself. and yeah. So you can do x2, x times x4 equal to x2 times x2, then x8 equal to x4 times x4, and x16 just equal to x8 times x8. So you see that you only need to do 4 multiplication to the x16, and compared to if you do brute force multiplication, you need to do 15 multiplications, right? So you have x 2, 3, 4, 5, 6, 7, 8, 9, 10 all the way to 16. Okay, so you see that this is much faster than doing brute force multiplication. Okay, and I guess we can talk about 4 minutes, and continual friction. I think this is too long, but we are going to flash over a little bit of the continual friction. Okay, and so this first part, you want to implement u sub x to the j very efficiently. Then you do repeated squaring, and you see that this is 2 to the j. Instead of doing order 2 to the j times, you only need to do j times to calculate the x to the 2 to the j. And the next one we do is we do continual friction to find the HO fraction here. Okay, and so the question is, you have some number that's very equal to s over r, and how you find s and r. And here we give some example. Okay, so maybe you the estimated phase you get is this thing 0.25001, and you think this is so by your human eyeball you think this is very close to 1/4. But how do you tell a computer to say this is 1/4? Then what you do is this continual friction is you write this 0.2501 as the friction. So 25001 over 100,000, and then you kind of flip things around. So you say this is 1 over something. So it's 1 over this 10,000 over 25001. And then you do division here with the quotient and the remainder. So you get a quotient equal to 3. And then you have 24997 over 25001. And you flip this fraction around once more, and you get 3 plus 1 over 25001 over 24997. And then you divide this thing once again, you have 1 plus 4 over 24997. Okay, and then you see that this friction now this get very small, and maybe I can throw away this part and it doesn't change too much. And so you just throw away this 4 over 24997 part, and so you change it to 0. And and then you see that this thing, if you throw away this small part, then you add everything back together, you get 1/4. Okay, and in general you can always write the continual fraction of your phi here, and cut off at some point. So at some point you think the remaining thing is very small, you throw it away, and you add the thing back, then you will get some fraction with a nicer number. Okay. And so this continual friction is you try to keep doing this thing and just start with some level, say the remaining part is 0, and then you reverse the calculation back, and you get some fraction. And so we don't go into detail, but basically we say that with the precision we have, with the 2L plus 1 precision we have, we can always find the S over R with continual friction. Okay. And so that's exactly on time. So let's continue with this. Continue with more detail of order finding next part, and then we'll pull it back and tell you about Shor's factoring algorithm. Okay. So see you on Thursday.